Let's now look at some compound inequalities where we actually need to isolate x first before we actually find the intersection or the union. So our first example, 2 times the quantity x plus 1 is less than 8, and negative 2 times the quantity x minus 1 is greater than negative 2. So to solve a compound inequality, we're going to have to individually solve the two parts and then union or intersect their sets. In this case, we're going to intersect them because of the word and. So we're going to solve this side first. 2 distributed in 2x plus 2 is less than 8. Subtract the 2 from both sides. 2x is less than 6. 8 minus 2 is 6. Divide out the 2 because it's positive. I don't change the inequality. X is less than 3. Now, we're going to eventually have an intersection of these solutions and the other side. So I want to distribute the negative 2 to the other side, the other inequality. So negative 2 times x. Negative 2 times negative 1 is positive 2. That's greater than negative 2. So negative 2x is greater than, well, if I subtract 2 from both sides, I get negative 4. And now when I divide by negative 2, I have to switch the inequality symbol. So x is now becomes less than positive 2 because negative 4 divided by a negative 2 is positive 2. So I get two statements here with an and in between them. So I have x is less than 3 and x is less than 2. So I need to think about what that would mean in terms of a picture. If x is less than 3, that means if this is 0, 1, 2, 3, that means I'm going to be less than 3. Whereas if x is less than 2, if I have 0, 1, 2, 3, here's 2, I need to be less than 2. Well, what do those have only in common if I'm intersecting them? Well, what they have in common is from 2 on down. So it would actually be this set. So my final result would just simply be to look at from 2 on down the page. Now, because I don't include 2 in this one, I also can't include 2 in my final answer. So the solution set would be from negative infinity to 2, excluding the 2. Okay, you can check that like we've done other examples, but this time you have to check all the way back and make sure that it works in both of those solution sets, or in both of those inequalities. So you would want to check, for instance, something on the left side that's actually in the solution set and something that isn't in the solution set, just outside. That would be a good way to make sure you've got the right result. I'll leave that check for you. Let's move on to the next example. 7x minus 6 is greater than 0, or negative 1/2 x is less than or equal to 6. Again, we're going to solve them independently and then take advantage of what that or is saying. That or is saying union the two solution sets that you get. So let's first solve this one on the left, add the 6 to both sides, so 7x is greater than 6, divide by the 7, x is greater than 6/7. Leave that as a fraction, don't try to change it into a decimal, it's not a nice decimal. Or then if we solve on the other side, I would want to multiply both sides by negative 2 to get rid of the fraction of negative 1/2. Now I'm going to get x, and because I'm multiplying by negative 2, I have to switch the direction of the inequality, so it becomes greater than or equal, and then 6 times negative 2 is negative 12. So we have x is greater than 6/7 and x is greater or equal to negative 12. In a union of those, let's just kind of do a quick sketch of both. This second one that we did, we'd be going from negative 12, including negative 12, and going all the way up. Whereas with 6/7 is between 0 and 1, I would be going from 6/7, but not including it, all the way up. Well, remember, we want all of both. This one is totally within the second set. So the second set actually is my answer. So the solution set is going to be the second solution set we got from the second inequality, because that contains all of what the other one had. So the solution set is from negative 12, including the negative 12, up to infinity. So brackets on the negative 12 because I want to say that it can be equal to negative 12. Our next two examples look a little different. In fact, we haven't talked about these types of inequalities. These are called double inequality statements. That's because you have two inequalities within the statements. Instead of having just a left and a right side, you have a left, a middle, and a right side. What's happening here is that you actually have an implied intersection. What this is saying is negative 3 is less than or equal to 3x plus 6, and 3x plus 6 is less than 9. Okay? It's an implied and when you see a double inequality in a statement, a left, a middle, and a right. It turns out it's easier to write as a double inequality and therefore solve because you end up doing exactly the same thing in both of these to get x by itself. So why not do it all at once in a single statement that has a left, a right, and a middle? But basically, another way to think about a double inequality is it's saying that this stuff in the middle, 3x plus 6, is between negative 3 and 9. So it's a way of saying when an expression has to have a low point and a high point. So it's saying that 3x plus 6 is between negative 3 and 9, and it can be equal to negative 3 because of the equal sign. So let's go back to the original and solve it. Negative 3 less than or equal to 3x plus 6 is less than 9. Again, what we can do is do the same thing instead of to both sides to all three sides, left, right, and middle. Now, what we want to do to solve and get x by itself is first subtract 6. If we subtract it from the middle, we have to subtract it from the other two sides as well. So I get negative 9 is less than or equal to 3x, which is less than or less than, no equals, to 3. Then, to get x by itself, we divide out the 3, and we're dividing a positive, so we don't need to worry about the symbols changing. Negative 9 divided by 3 is negative 3, is less than or equal to x, is less than 1. So what this is saying is that x is between negative 3 and 1, and we include the negative 3 but not the 1. So the solution set would be negative 3 with a bracket up to 1 with a parenthesis. Okay, so this is called the double inequality. We have a second example here. Negative 3 halves is less than 4 minus 2m is less than 7 halves. Sorry, computer freeze for a second there. I think we're back to normal. Now this has a fraction. What I would recommend you do at first is clear those fractions. So we're going to multiply everything by 2. 2 times negative 3 halves is less than 2 times 4 minus 2m is less than 2 times 7 halves. Remember, if you're going to multiply by 2 on one side of the statement, you have to do it to all sides. In this case, not just the left and the right, but the middle as well. So the 2 clears this denominator, so we get negative 3 is less than 8 minus 4m, when I multiply through by the 2, is less than, and the 2's cancel here, so we just get 7. Now, slowly get the m by itself. So I want to subtract 8 from all three sides. So I get negative 11 is less than negative 4m is less than negative 1. And now I'm going to divide by a negative 4. Now when I divide by a negative 4, technically I've got to switch those symbols at the same time. So I'm going to do that on the next line, switch the symbols. This is going to become greater thans, m in the middle, and I get 11/4 on the left, and on the right I get 1/4. So notice what this is saying, because the symbol switched. 1/4 is less than, I'm reading it this way, 1/4 is the smaller number, it is less than m, and m is less than 11/4. So this is saying that m is between the numbers, low number of 1/4 and the high number of 11/4. So the solution set, and we always start with the low number with the solution set, would be from 1/4, positive 1/4, up to 11/4. And I accidentally put a bracket there. Let's just erase that because there is no equals. So I should have a parenthesis on both. So 1/4 up to 11/4, not including either sign because there is no equals on either side of this double inequality.